Hi and greetings everyone, my name is Naqib Syahmi and I'll be presenting along with my group members our group project titled Optimizing Crop Yield Through Big Data Analytics in Precision Agriculture. So my other group members are Madina, Harith, Sultan, Adibah, Izzati, Tanisya and Yuhan. The agriculture sector faces mounting challenges such as climate change, resource scarcity, and rapid population growth, which necessitate the adoption of more efficient and sustainable farming practices. Therefore, to address these challenges, precision agriculture emerged as a transformative approach that integrates advanced technologies such as big data to optimize agriculture productivity and resource use. Big data in precision agriculture refers to the collection, integration, and analysis of large and diverse datasets from multiple sources, such as satellite imagery, soil and weather sensors, and historical crop records to support data-driven decision-making. By leveraging big data analytics, precision agriculture enables farmers and agronomists to interpret complex environmental and operational variables, leading to more accurate prediction of crop performance.
Problem statement 1, data quality and processing. Basically, large-scale crop yield data comes from surveys, records, and sensors. So the raw data often has missing and incorrect values. So poor quality can affect analysis and reduce prediction accuracy. This can lead to wrong in conclusion and poor decisions. In this study, Apache Peak is used to clean, validate, and standardize large crop yield data stored in HDFS. Problem statement 2, large-scale crop yield analytics for optimization. Crop yield depends on weather, environment, farming methods, and region. Finding useful patterns with traditional methods is difficult. Large-scale data needs fast and scalable processing tools. So this study compares Hadoop streaming, MapReduce, and Apache Spark, PySpark for crop data analysis. So now, let's see about the dataset. The dataset contains crop yield records from different regions. Each record represents one crop along with its environmental and farming factors. The dataset has 1 million records and 10 attributes. This include region, soil, crop, weather, temperature, and so on. Okay, let's go through the workflow. First, we uploaded raw crop yield data into HDFS enabled in a distributed storage and processing. Then we cleaned, validated, and standardized data, executed peak scripts using Yarn. Then we stored clean data in HDFS, ensured reliability and readiness for analysis. Next, we performed batch-oriented processing using MapReduce, analyzed crop yield patterns parallelly. Then we performed fast in-memory analytical processing using PySpark, supported aggregation, filtering, and scalability. Then we analyzed factors in large scale. And finally, we compared Hadoop streaming and PySpark, and then evaluated speed, throughput, and scalability. Performance evaluation metrics. Processing speed, average runtime, measures the total time to complete a task, includes data loading, processing, and output, shows overall system efficiency. Data throughput measures how much data is processed per unit time. Higher throughput means better performance, calculated as data size divided by execution time. Scalability, runtime per MB, shows how performance changes as data size grows, calculated as runtime divided by data size. Lower value means better scalability.
Data preprocessing has been done using Apache Peak. So at the left-hand side, which is the script that we've been using for data preprocessing using Peak language. So initially the data size was 1 million records, and then after preprocessing, it reduced approximately 0.02%, involving removal of invalid or inconsistent records and also duplicate records. So in terms of performance for Apache Peak, the processing speeds for Yarn reports execution time of approximately 18 seconds, while Peak console reports longer runtime, which is around 3 minutes. So this difference are due to script passing, job submission, and also communication overhead by the Peak console, while Yarn time reflects only the core MapReduce execution space. In terms of scalability, the runtime per MB is around 0.2 seconds, so the performance remains stable on a single node cluster, and scalability can be improved further in a multi-node environment. So in terms of data throughput, the input size was approximately 89 megabyte, and it achieved a throughput of around 4.95 megabyte per second without any errors.
This slide presents the analytical results from both Hadoop streaming and PySpark on the impact of weather conditions on crop yield. Crop yield was analyzed across cloudy, rainy, and sunny conditions combined with different soil types. And across most soil categories, sunny conditions consistently produced the highest average yields, while rainy conditions resulted in moderate yields and cloudy conditions produced the lowest yields. Importantly, these patterns were consistently observed in both Hadoop streaming and PySpark outputs, indicating agreement between the two distributed frameworks. Based on these results, we can see that weather conditions play a significant role in influencing crop yield, mainly through variations in sunlight exposure and water availability. The persistence of yield differences across weather conditions, even when soil type remains constant, suggesting that weather exerts a strong influence on agriculture productivity. The consistent trends observed across soil types and across both processing frameworks highlight the importance of weather-aware decision-making in precision agriculture.
For the next step analysis, role of environmental factors, it repeats person question and head streaming, to quantify the relationship between climatic variables by the results and statistically rainfall exhibit a robust by the results statistically rainfall shows a strong correlation with yield 0.76, while temperature shows a weak correlation of 0.0808. The results from the platforms are consistent, demonstrating computational evidence between the two frameworks and validating rainfall as the predominant determinant of yield. For conclusion, the role of environmental factors in crop productivity, we evaluated rainfall and temperature as key influencer of crop productivity. Our analysis reveals a distinct hierarchy where rainfall demonstrates a strong positive correlation with yield, while temperature shows a comparatively weak association. We can conclude that water availability is the dominant environmental determinant. The same results produced across both PySpark and Hadoop streaming shows that these findings are robust, strictly data-driven, and platform-independent.
This slide presents the analytical results from both Hadoop streaming and PySpark on the effectiveness of agricultural practices, namely fertilizer usage and irrigation on crop yield. The crop yield was analyzed across 4 conditions. Condition 1, where no fertilizer and no irrigation were used, produced the lowest yield, approximately 3.305. Condition 2 and 3, where only either fertilizer or irrigation were used, the yield showed moderate improvement from the baseline, with scores of approximately 4.799 for fertilizer only and 4.499 for irrigation only. Condition 4, the usage of both fertilizer and irrigation produced the highest yield, approximately 5.999, which almost doubles the baseline statistics. From this analysis, we can note that agricultural practices significantly improve crop yield. The usage of fertilizer alone is slightly more effective than irrigation used alone. However, although individual interventions positively contribute to the yield improvement, the combined use of fertilizer and irrigation delivers a strong synergistic effect and proves more effective for crop yield.
Lastly, we do the analysis on crop productivity across regions using the Hadoop streaming and the PySpark. We found that the temperature and days to harvest are similar across regions, but rainfall and crop yield vary significantly. This shows that the water availability is the key factor behind the regional yield differences. So the both platforms produce consistent results, allowing us to clearly identify the high yield and low yield regions. The top screenshot here is the result coming from PySpark, and this bottom screenshot here is the result coming from the Hadoop streaming. These consistent results from both platforms confirm that our big data framework is reliable. More importantly, it allows us to identify high productivity region at scale, which support better planning for irrigation, farming input, and resource allocation in precision agriculture.
Now, let's look at the specific performance breakdown for each framework. On the left, we have the result for Hadoop streaming. We observe that for the heavy region-based aggregation task, processing about 93 megabytes of data took nearly 2 minutes and 24 seconds, resulting in throughput of just 0.65 megabytes per second. However, performance did improve significantly for the lighter agriculture practice task, where the runtime dropped to about 16 seconds. On the right, we have PySpark, which executed queries on a similar dataset of roughly 89 megabytes. The speed advantage here is clear. Most of the tasks were completed in just 0.8 to 1 second. Moving on to direct side-by-side comparison of Hadoop streaming and PySpark, we conducted this testing using 4 analytical tasks, measuring processing speed, data throughput, and scalability. The result highlights a significant performance gap. If you look at the first row, the impact of the weather condition on crop yield, you will see that Hadoop took roughly 150 seconds to complete the task. In contrast, PySpark finished the exact same analysis in just 0.9 seconds. This trend holds true for the other tasks as well. While Hadoop processor time varied, reaching 144 seconds for the original reference task, PySpark remained incredibly consistent, completing almost every task in roughly 1 to 2 seconds. Hadoop streaming relies on a disk-based MapReduce execution model. This approach naturally creates higher input-output overhead during intermediate processing because data is frequently written to and read from the disk. However, it remains reliable just for stable batch-oriented workload. PySpark, on the other hand, utilizes an in-memory computational model. By keeping data in memory, PySpark achieves faster execution and better scalability, making it optimized for iterative and time-sensitive analytics. The key takeaway here is that while both frameworks produce consistent analytical results, they differ significantly in performance.
To conclude our project based on results and discussion, big data analytics effectively supports precision agriculture with our Hadoop-based framework that enables scalable crop yield analysis. We were able to identify that weather conditions, rainfall, and agricultural practices significantly influence crop yield, and the overall performance from our implemented frameworks highlights that PySpark evidently outperforms Hadoop streaming in performance metrics. A couple of key takeaways from our project is that rainfall appears to be the most influential environmental factor that influences crop yield performance, and the combined fertilizer and irrigation yield the highest productivity. From our implemented framework, PySpark is best suited for time-sensitive analytics, while Hadoop streaming is for high-latency analytics. Overall, big data enables data-driven agricultural decision-making. Future work that our group could potentially explore in our project is to extend the framework with advanced machine learning models for crop yield prediction and optimization, and most importantly, to integrate real-time agricultural data analytics to support timely decision-making. So thank you for listening to our group project.
Thank you.
Thank you.
Thank
Thank
you.
you.
Thank
Thank you.
you.
Thank